Hello everyone. This is week 10, and in this week, we will try to solve some sample problem. So, let's see. You can see that there is a problem where it is saying that there is a one element triangular mesh which is shown in figure, and the edge BC is constrained to move in y direction and free to move in x direction, and AB is constrained to move in x direction, and it is traction free in y direction. The edge AC is subjected to traction normal to the edge shown in figure, and assume the Young's modulus, Poisson ratio and everything. But first it is saying to construct a weak form to the corresponding problem, and also to create a generalized boundary condition, and to construct a stiffness matrix, global force matrix, and to solve for the unknown displacement and stresses at point 1.5. So where it is 1.5, 1.5 will be somewhere here. So what will be this length? This will be 3 root 2. Root 2. And what will be this height? This height will be, sorry, yeah. Okay, first see where 1.5 is, then we will solve it. Suppose what is the midpoint? If I talk about the midpoint, so here it is a midpoint, and this length is 3 root 2, and what will be this length? This length will be 3 root 2 divided by 2, which is nothing but 3 divided by root 2. And since the angle is 45 degree, so what will be this length? This length will be 3 by root 2 into cos 45. This means that 1 by root 2, and that will be 3 by 2, that is 1.5. So which means that the midpoint will be somewhere here. Will be somewhere here. I mean on the hypotenuse where it is bisect this hypotenuse. So yeah. But yeah, we don't have to create a mesh because this is already a mesh, and by using the interpolation we have to find the stresses at point 1.5, 1.5. So first let's see what it is saying. It is saying that to create a weak form, so we already know that what is the equilibrium equation. Equilibrium equation is delta dot sigma plus B equal to 0. And if we take the weighted residual of this equilibrium equation, then we get omega delta dot, and since it is second order tensor, plus B vector. So let's create a vector here. Yeah, B vector dot W vector into omega equal to 0. So this is the weighted residual. Now if we break this, then it becomes something like this. Now we will use the property of divergence, that is delta dot sigma dot w is delta bar dot sigma dot into w bar plus w del w dot sigma. Okay, so here this is the divergence property. Okay, now we can directly use here, so that becomes here it should be plus. Okay, if I write here, I mean the left hand side first, then it becomes okay. So here we will use the Gauss divergence theorem, so that we already know that the divergence of f vector will be given as here I will use S to show the surface integral. Okay, so what will be the result? Result will be del bar w dot del omega, and so this will be dot this dot n ds plus this will be as it is. Okay, so create some more space here. Now we will use one property, that is, if you already know that that sigma dot this dot n can be written as w dot sigma bar dot transpose n vector. So here we can directly use that, and also we have to use one more thing, that we already know that sigma double bar equal to d, and here it will be 4 times bar, so d double contraction and strain. Double contraction, strain. And there is one more thing. What is that? The gradient of u vector, we already know that we call it as a strain tensor plus rotation tensor. We already know that. And if you take the double contraction with the stiffness matrix with this gradient of u, it becomes and here that epsilon bar is nothing but the symmetric part of, this is symmetric part of gradient of u, and that omega tensor is nothing but the skew symmetric part. Okay, and there is one property that is called, if you take a contraction with the double, the double contraction with the symmetric tensor, with the skew symmetric tensor, then that part becomes 0. So that's why we can directly use this thing as this, which means that I can write okay. So this is one thing and this is another thing. Okay, so these two things we need to use it here. So we get that sigma bar, we will use it, and this is what there is yeah, this thing we can also write it as a sigma tensor. So that is d dot, that we can also write it as a dot, or we can also write it as a contraction, so nothing to worry about it. So whatever it will give a second order tensor. So I can also write it as a like this, so it won't matter what we are representing. Okay, so this will be d omega, and this thing is what, this thing will become line integral. So you can see that, so that will be, and yeah, we can also, yeah, here this will become f dot nds, so which means that sigma dot omega dot n ds, and this term will be as it is, that is double integral b bar, and this is also a bar, b bar dot omega bar d omega, and this is what, and here we will use one property, without that also we can use it, but yeah, so this is all about that is this dot and yeah, this is there is one more property we can use it here, that is w dot sigma transpose n vector ds plus b dot. So yeah, we arrive at our final result, that is and we already know that this is nothing but the traction. So yeah, so this is the all about, I mean if I want to write in terms of matrices, then yeah, this is in the vector form. In the vector form. If I want to write in the matrix representation, then we can also write it like this. Delta W into so this is the representation in the matrix form. And here this is what, either you can write W transpose dot n or transpose dot t or t transpose dot, it won't matter, so it will become dot t ds plus this is what B transpose dot W, or I mean it won't matter, all are vectors, so we can also write transpose B ds. So this is in the matrix form. So yeah, so this is the weak form of our problem. Okay, weak form. Okay, now this was the first part. Now it is saying construct the stiffness matrix. Okay, so let's construct the stiffness matrix. But first we need to see what will be the size of the stiffness matrix. Okay, so what will be the size? There are 3 nodes, which means that n equal to 3. So which means that the size, the dimension of k global, what will be that? That will be 2n, 2 times n, that will be 6. Okay, and the dimension of force matrix, that will be global, that will be 2 into, yeah, okay, so 2 times n cross 2 times n by 2 times n, and here it will be what? 2 times n by 1. Okay, now let's construct the stiffness matrix. But we can see that here that D is a 4th order tensor, which means that how many components will be there? There will be 3 by 3, 3 by 3, there will be 3 by 3 into 3 by 3, there will be 81 components. But because of that, this is isotropic, we are assuming that this is isotropic material, which means that using all symmetries, this will be reduced to 2. Okay, and after reducing, we can write this 4th order tensor as only, we can write as a second order tensor for 2D problem. For 2D problem, we can write what? For 2D problem, D will be only 3 by 3 matrix, and what will be that? That will be E divided by 1 minus nu square divided by, what will be that? That will be, I think if I'm not wrong, that will be 1 nu 0 nu 1 0 and 0 0. I think that will be, yeah, wait, I need to see it. What is that? 1 minus nu by 2. 1 minus nu by 2. Okay, so in this case you can see that this is only a 3 by 3 matrix. So how we will do, how we will construct the stiffness matrix based on this. So here there is a catch that sigma, that is sigma is also a, since it is a plane stress problem, so sigma is also what, 2D. So which means that the dimension of the sigma will be only like sigma xx, sigma yy, and sigma xy. It will be something like this, and this will be what, this will be 1 nu 0 nu 1 0 0 0 1 minus nu by 2. Okay, I missed here, that is E divided by 1 minus nu square, and it will be 1 nu 0 nu 1 0 0 0 1 minus nu by 2. And here it will be what, epsilon xx, epsilon yy, and 2 times gamma. Okay, or we can also write as epsilon xy. Okay, and what is the epsilon xx? Epsilon xx is nothing but del u by del x. And what is epsilon y? That is del v by del y. And what is 2 gamma, or you can say epsilon xy, that is nothing but del u by del y plus del v by del x. Okay, so now but here the problem is how we will represent that the second order tensor. See, this is also second order tensor, this is a first order tensor, but how we will represent it. Okay, so now we will try to build based on the shape function. So let's assume that u equal to, that is u1 n1 plus u2 n2 plus u3 n3, and similarly v is what, that is v1 n1 plus v2 n2 plus v3 n3. Okay, we are assuming to be like this. So what will be the du by dx? Okay, because we need to find the du by dx. So what will be the du by dx? That will be du by dx, or we can also write here. Okay, so what will be the du by dx? So du by dx I can write something like this, that is n1x, n2x, n3x. Okay, and this will be what, this will be u1 u2 and u3. Similarly, what will be dv by dx? dv by dx will be same thing, sorry, dv by dy, it should be dv by dy. dv by dy will be what, n1y, n2y, n3y, and this will be what, v1 v2 and v3. Okay, and what will be du by dy plus dv by dx? Okay, that we need it. So what we can write, that will be, if I create a matrix, then du by, the whole thing, first we will write something. Okay, we will create a matrix later. Let's do something like this: u1 n1y plus u2 n2y plus u3 n3y. Okay, and plus v1 n1x plus v2 n2x plus v3 n3x. Okay, now I want to combine Okay, if I want to write this thing in a matrix form, then how we can write it? Let's see. If I want to write this whole thing in a matrix form, then how I can write it? So I can write n1y n1x plus n2y n2x, and similarly n3y and n3x, and in the matrix it will be u1 v1, u2 v2 and u3 v3. Now if I combine these three, if I combine this, if I combine this and this, then it will form a delta y. Okay, if I combine these three, then it will form a delta y. So delta y, not delta y, it will be delta u. So what will be that? Del u by del x, del v by del y, and del u by del y plus del v by del x. And this will be what? This will be, I can write here n1x plus 0, n2x 0, n3x 0. Okay, and so there will be how many entries? 1 to 6. So 2 to 6. Yeah, now it will be n1y 0, n2y 0 and n3y. Okay, 6. Now what will be the third entry? n1y, n1x, n2y, n2x, n3y and n3x, and here it will be what? u1 v1, u2 v2, u3 and v3. Now we got delta u. Okay, so this thing is very important, and this is what? Stiffness matrix. So now I can write what? Delta u as a terms of this. Okay, and suppose we are not if we are writing shape function as same as, I mean, we are not representing in terms of zeta and eta, then we can use it as a b. We can use it as a b. So this is b. So we can write that b, this is not a vector this time, b times u. Okay, so this thing is that. Now what else we left? Yeah, so everything is done. We can directly use it as, yeah, w. What is w here? W is simply n. Okay, w is simply n, and what is that? Delta w. Delta w is same as that will be b w bar. Okay, so if we combine everything, and also yeah, if we combine everything, then what we get from the main equation? So we can get delta w, that will be b w transpose, and it will be what? D times and delta w, so that will be b u hat. Okay, equal to, and here it will be what? N transpose T ds plus, and it will be what? N transpose bi. So that will be N transpose, yeah. So here also, yeah, w equal to, we can write at n and yeah, w and yes, n w. Okay, so yeah, n transpose. Okay, I forgot here to write. So what is that? n w bar. Okay, n w bar dot t, or we can say that, yeah, it will be a transpose t ds plus, and this will be what? This will be nw transpose bi. Okay, so b del omega. So it will be a double integral. Now what will be this? This will be w bar transpose b transpose, and this will be d and b del omega. Okay, and this will be what? And yeah, u will be come here, and this will be what? This will be w hat transpose, and I will write in the matrix form here, and in vector form here, and yeah, it will be single integral now, and it will be w transpose, and not w transpose, it will be n transpose t ds plus, and yeah, w transpose hat, and it will be n transpose b del omega. Okay, so because of the arbitrariness of the w hat transpose vector, so we can write it as b transpose db del omega. And this will be what? This will be n transpose t ds plus n transpose b d omega. So we already know that this will be nothing but stiffness matrix. So that will be K, and this is the U, and this whole term is F. So we can write it as a KU equal to F. So I mean, I have derived it again. So because the problem is demanding that. Now it is saying to construct the stiffness matrix. So first we need to find what is the shape function. Okay, so what is the shape? Shape is a triangular 3 3 3. Okay, so here shape is something like this. So this is the 0 0, this is the 3 0, and this is the 0 3. So here we have to find the shape function. So we already know that how to find the shape function. So that is ax equal to I, and x will be a inverse. Okay, and the entries will be the solution. I mean, the entries will be the solution of transpose of that. Okay, and what is the a inverse? A inverse, we can write it like this. What is first? I want to write what is a. So a will be 1 and this coordinate, that will be 0 0. Okay, and that will be 1 3 0, and this will be what? 1 0 3. Okay, and now I want to find the a inverse. So a inverse will be adjoint of a divided by determinant of a. And what will be the adjoint? Adjoint will be the transpose of the cofactors. So if I talk about this will be 9, and this will be, if I remove this, so this will be 3, and this will be -3. Okay, and this will be this will be minus 3. Yes, minus 3. And if I talk about this thing, if I remove the rows and columns, so this will be 0. If I remove this will be 3, and if I do this will be 0, and if I do this will be 0. For this it will be 3, and 3, since it is a 3 2, so it will be minus 3, so it will be 3. Okay, and it will be transpose. And what is the determinant? Determinant of A will be 1 times 9, so that will be 9. So I have to write 9, and this will be what I have to write the transpose. So transpose will be 9 minus 3. I mean, even if I not write the transpose, okay, let's write the transpose. 0 3 0 0 minus 3 3 divided by 9, and this will be what? A inverse will be 1 0 0. This will be minus 1 by 3, 1 by 3, minus 1 by 3, minus 3, minus 1 by 3, 0, and 1 by 3. So what will be the shape function? Shape function will be the transpose of that. So which means that n1 will be 1 minus x, n will be 1 minus that will be x by 3 minus y by 3. And what will be n2? N2 will be this, so that will be x by 3. And what will be n3? N3 will be, so this should be, I think, wait, maybe I am making mistake here. 030, okay, 03, that will be 9 minus 3, okay, it should be 0 here. Should be 0 here, so 933 0, and I think here it should be, yeah, it should be 0, and this will be 0, and this will be 0, and this will be what? This will be 3. I think here the first entry will be what? 0. Yeah, here it is a mistake. It should be 3. And here what should be what? 9 3 3, okay, 933 0 3 0, okay, here it is a wrong entry, 003. Okay, so it will be transpose of this will be here, it should be a 0, and here it will be 1 by 3 and y by 3. So now this is the shape function, we can use it. Now we can verify it. Yeah, so if we substitute x equal to 3 and y equal to 0, so we can see that it is 0, and if we substitute 0 3, it will be also 0, and for here 0 0, and if we substitute x equal to 3, that is 0 and 0, yes, yeah. So this is the shape function. Now what will be the b? So based on that, what will be the b? Okay, now we can use our code directly and we can solve the problem. Okay, so let's move to the MATLAB program and we will think I have already created one MATLAB code, that is assignment number 9. No, assignment number 10, I think. Yes. So here, I mean, it is very similar, but yeah, boundary condition is little different here. So what is the nodal coordinate? Nodal coordinate is 0 0 and it is 3 0. 3 0 and 0 3. And here we need to write the Nyman boundary condition, and Nyman boundary condition is constant, and that is in this direction. So here I will remove this because there is no use of that. So here it is what? In the vertical, I mean for this plane it is vertical direction. So if I resolve in x and y direction, so it is 15 and it will be 15 cos 45 degree, 15 sin 45 degree. So 1 by square root 2 into into 15, and here also 1 by square root 2 into 15. Okay, and this is the edge number 2, so that's why I have created this. So we are using the order 2, I mean point 2, 1 2 3, that is fine. Let's see the B matrix. What is the B matrix? So first I have to create this thing, that is, what is the B matrix? B matrix, based on this, what is B matrix? Let's find the B matrix. B matrix is n1x 0, n2x 0, n3x 0, okay, and 0 n1y 0, n2y 0, n3y, and here it is what? n1y, n1x, and n2y, n2x, and n3y, n3x. Okay, so based on that I have created, first we need to find n1x, n2x. So this is all about that. So what is that? That will be 1 by 3. So here it will be 1 by 3, and it will be minus 1 by 3, and here minus 1 by 3, 0, and 1 by 3. Here it should be plus 1 by 3. Okay, so yeah, I mean there is no use of this Jacobian, I mean this inverse transpose, because anyhow it will give the same answer. So nothing to worry about that, because there is no such case of yeah, we can directly use that, because this inverse Jacobian is anyhow the identity matrix, so nothing to worry about that, because there is no such giant. Okay, let's remove this part. we can directly use it. So what will be the first row? First row will be this data 11, data 11 0, data 12 0, and data 13, and here it will be what? Same thing, we will just replace it from everywhere. Okay, so this is, I mean, yeah, there is no use of it, so let's remove this. Okay, if I want to get the output of this, then it will give it. So yeah, this is the B matrix, so you can see that. Now, so B matrix is ready. Now if I go to the stiffness matrix, so everything is fine. Yeah, here we need to change the data, because what is the value of nu? Nu is 0.3, and what is E? E is 3 times 10 11. Okay, and C is same. Jacobian, what is Jacobian? Yeah, here we also we need to change it. That will be minus 1 by 3, 1 by 3, minus, okay, 1 by 3, it will be 1 by 3 by 3. Shape function is and there is no use of the shape function here, so anyhow if it is required, I mean, there is no use of it, so let's skip it. Okay, let's yeah, let's suppose three minus 1 by 3 divided by 3 minus x minus y, and 1 by 3 So this is all about the shape function, and Jacobian is fine. B matrix is also fine. Okay, let's see the stiffness matrix. So what will be the function? The function will be determinant of J transpose B C and B transpose, and here the integration that will go, if I see this, then integration which should go from x equal to 0 to x equal to 3 minus y, because the equation of this line is 3 minus y. So that's why, so we need to write 3 minus y, 3 minus y, and y will go from 0 to 3, y will go from 0 to 3, and what else? Yeah, everything is correct now. Now we can run this code. Let's see the force matrix. Okay, so the force matrix we have normalizes, that is fine. Bottom, yeah. So if I see the bottom, if I see the bottom edge, then for the same function will be what, y equal to 0, and x will go from, x we will substitute as s, and if I see the slant will be y will go from 3 minus 3 minus, anyhow we can write y equals y equal to 3 minus x, and x should flow. If I see something like this, suppose this is s, okay, so what will be that, since the angle is 45 degree, so this will be s cos 45 degree, and what will be this will be 3 minus s cos 45 degree, so that will be 3 minus, this will be 3 minus, because we are doing the integration on this path, so that's why this will be, the shape function will be this, okay. And for the left hand side, for the shape function on the left hand side, that will be x equal to 0 and y will run as it is, okay. So this is all about that, and yeah, now we will integrate it, and for the base, it will integrate from 0 to 3, and the slant is, it will integrate 0 to 3 root 2, okay, and this will be 3 to 0, okay, and then it will do same as it is, and yeah, now if I go for the boundary condition, okay, for the boundary condition, so in this case, what is that, the boundary fixed nodes are, okay, let's see for the okay, what will be the fixed nodes will be, okay, let's create some space here, and then we will see the fixed nodes. Fixed nodes, okay, then here we can see that this thing can go yeah, so let's mark first, then we will see this, okay. So this is u1, v1, u2, v2, u3 and v3, okay. So for node 1, if I talk about node 1, then it cannot move along this direction, yeah, it can move along this direction, but it cannot move along this direction. What it is saying, first we need to see this, the edge BC is constrained in y direction, BC is constrained in y direction, which means that v1 is also 0, and v2 is also 0, is constrained in the y direction. Now it is saying that where the edge AB is constrained to move in x direction, okay, it is moved along x direction, so it is free to move along x direction, and the edge AC is subjected to, yeah, so the only the displacement boundary condition is along this. So what will be the free nodes, that will be 1 2, this is 2, okay, this is 2, and this is 1 2 3 and 4, which means that fixed nodes are 2 and 4, which means that fixed nodes are alpha 2, alpha 4 equal to 0, okay. So because this is constrained to move in vertical direction, it can move along the horizontal direction, but it cannot move into the vertical direction. And also this thing v3 is also 0, V3 is also 0 because it cannot move in the vertical direction. So that's why 1 2 3 4 5 and 6, so alpha 6, which means that 2 4 and 6 will be 0. Okay, 2 4 and 6 will be 0. So here I need to write 2 4 and 6. 2 4 and 6, it is a fixed node, it cannot move along the vertical direction. Okay, 1 to 6, 1 to 6 fixed nodes. We can see that there is no displacement along the fixed nodes. Okay, so yeah, now I can run this code. So after running this code, okay, let's see what is the result we are getting. Okay, B matrix 2. Okay, stiffness matrix actually we are giving Jacobian. There is, yeah, there is a coordinate. In B matrix there is no coordinate because we are not providing it. It is constant. Let's run this code. Yeah, so we can see that this is the global stiffness matrix, which is what it is asking first. Okay, this is what it is asking first. So this is the global stiffness matrix, this is the stiffness matrix, and what is the force matrix. So this is the, okay, let's display the force matrix. I have not displayed yet. Yeah, I have already displayed. This is the global, yeah, this is the global force matrix. Now it is saying solve for the unknown displacement matrix and calculate the stress at point 1.5. So what we got here is the displacement we got here is something like this. This is the displacement we got, and this is u1, v1, u2, v2, u3 and v3. Okay, and if I see this, then it is saying it will move along, this node will move along this direction by some magnitude, this direction by some magnitude, this direction by some magnitude. This node will also move by some magnitude. Okay, and there is one more thing we need to understand, that it is saying, if I see this, it is saying that it is constrained, that only the edge AB, only the edge AB is constrained to move along. Okay, BC is constrained in y direction, okay, fine, and traction free, whereas AB is constrained in x direction. AB is constrained in x direction. So if I see like this, it is saying okay, AB is constrained in x direction, which means that if I talk about this, which means that U3 is also 0. U3 is also 0. V3, I mean this is not constrained in vertical direction. This, I think we have done some mistake, that this node, this whole AB is constrained in x direction, which means that U3 will be 0 and U1 equal to 0. And also it is saying the BC is constrained in y direction. BC is constrained in y direction, which means that V1 equal to 0 and V2 equal to 0. What does it mean? This is what it is saying, V1 equal to 0 and V2 equal to 0. So this is what, so what we remained, yeah, so that is 1, I mean that is 2 and 4, 2, 4 and 3 is also 0, okay, 3 is 0, but this will remain 1, 2, 3, 4, 5. 2, 4, 5 is constrained, okay, but this will remain. So that is 2, 4, 5, not 2, 4, 6. We didn't read the problem carefully, so that will be 2, 4, 5, okay, because if I see like this, I mean 1, 2 and this is 3, 4 and this is 5 and 6, then it is saying that this face AB is constrained to move in x, which means that this 1 and 6 will be constrained, so that will be fixed nodes will be 1 and 6, 1, 6, and also the face BC is constrained in y direction, so which means that 2 and 4, so 1, 2 and 4, so which means that only 3 and 5 will survive. Now it is fine, okay, so that will be U, yeah, 1, 2, 4, 1, 2, 4, 5, 1, 2, 4, 5. Now okay, 5 here, 5. Now it is fine. 1 and 5 is constrained, 2 and 4 it is constrained, okay. Let's run this code. Yeah, so which means that we get the displacement like this. So this is the displacement, which means that 1, 2, 3, 4, 5 and 6, which means that this will remain as it is. This will also, I mean there is no motion for this node, this will move along x direction, that will be this, and 4 there is no vertical motion, and here it will be a vertical motion, so which means that here it should be, yeah, I mean this is all about that. Now it is saying, what is the next problem? Next problem, it is saying solve for the unknown displacement matrix and calculate stress at 1.5 and 1.5. okay, so let's find how to, yeah, unknown displacement matrix, that is fine. Calculate the stress at point 1.5 and 1.5. So to find the stress at which location, it is saying sigma at 1.5 and 1.5, and we already know that u and v, we already know that u1 n1 plus u2 n2 plus u3 n3, and this is what v1 n1 plus v2 n2 plus v3 n3, and if you substitute x equal to 1.5 and y equal to 1.5, then we will get u and v. Okay, but to find the stress at point at x equal to 1.5 and y equal to 1.5, what we have to do? First we need to find the delta u, and we already saw that that will be b times u. So if I find, so that will be b times u, and we can see that b is constant. We already saw that b is already a constant matrix. B is a constant matrix, so if you import like b equal to B matrix, then it is a constant matrix. Okay, now if you multiply del u equal to B matrix, what is that? What is the size? The size of B matrix, size of B matrix is 3 by 6, and what is the size of u? The size of u is 1 by 6. So what we got it, yeah, we can check it, size of u, and that is 6 by 1. Okay, that is 6 by 1, that is 6 by 1. So which means that if you multiply directly, then we will get delta u. So let's multiply it, b times u. Okay, then we will get delta u, and it is not a function of x. You can see that it is not a function of x. And now if you multiply sigma, if you multiply the sigma at, I mean it is also a constant, so sigma will be d times, and what is that d? D we have not imported, so d will be, so let's multiply here. I think we have used it already in the stiffness matrix, I think, yeah. So this is d. Okay, and what is nu here? Nu equal to 1 by 3, and what is E here? E equal to stiffness matrix, that is 310 this, so 310 this. Okay, so E here is done, nu is done, so sigma will be directly multiplication of d times del u. Okay, so let's see the result. okay, new, okay, yeah, here it should be new. Okay, here we can see that at location 1.5 and 1.5 is 15.75. Here you can see that it is not a function of x, which means that at every location inside the triangle, the sigma will be constant. So that's why the stresses, because B matrix is also independent of x, so everywhere this sigma will be a constant, that will be 15.75. so this is the answer. So which means that sigma x at that location is 15.75, sigma y will be 15.75, which means that at this location, if I see like this, then it will be something like this. Okay, sigma x, sigma y, sigma x and sigma y. So this is all about this problem, and then we will solve the second problem. Now the next problem is to solve the same elasticity problem, but we have a trapezoidal domain where there is a vertical traction is acting in downward direction on this edge, and this edge has a displacement boundary condition which is fixed, and everything is already given. And now it is saying that we have to discretize is using a quadrilateral element, and we have to solve the problem. Okay, so in this problem also we will use the same methodology, same variational statement. What is that? We will just copy and paste this thing. So we will use this variational statement for this problem. So where B, we already saw that what is B, and D is the stiffness. D is the constitutive equation, and B already we saw that what is B. This is B. This matrix is B, and everything is already known. But here there is a little bit difference, because whatever we are choosing for the shape function, earlier it was a function of x, but here since we are changing from the physical domain to the master domain, so the shape function will be a function of xi and eta in this case, which means that suppose we are discretizing the domain like suppose this is node number 1, node number 2, 3, 4, 5, 6, 7, 8. Okay, and suppose we are taking this element, this is suppose this element number 1, 2, 3 and 4, and if we take this element, and since the coordinate, if I take coordinate axis is like this, x-axis, y-axis, and this length is 0.5, which means that this height is also 0.5. So this length, this coordinate will be 2, 0.5, and the coordinate of this point will be 2, 1, and this will be 0, 1. So suppose the coordinate, this will be 0, 0, and if I take the element number 1 and this is node, the global node 1, 2, 5, 4, and local node is, I am taking it as a 1, 2, 3 and 4. And suppose the coordinate, because based on this the coordinate will be 0, 0, and suppose this is so 1, 0.25, and this will be, suppose 1, and this height is what, 1, so I am taking 0.75, 0.75, and this will, I suppose, 0, and this will be little bit lower than this, so I guess it should be 0.65. It's just a random guess. So, and in the master domain it will be like this. So this will be -1 to 1, so -1 to -1, and this will be 1, -1, this will be 1, 1, and this will be -1, 1, and here it will be origin. Okay, so based on this will be 1, 2, 3 and 4. So based on this we have to write x equal to x1 n1 plus x2 n2 plus x3 n3 plus x4 n4. Similarly, y will be y1 n1 plus y2 n2 plus y3 n3 plus y4 n4. Okay, but here ni will be a function of xi and eta. Okay, now we have to find what are n1, n2, n3 and n4. So based on this, since this is a quadrature, so what will be n1 here for node 1, the shape function when for node 1 when n2 the n1 will be 0 at 2, 3 and 4 position. So we already saw that will be xi minus 1 and eta minus 1 divided by what, -1 and -1. So it will be 1/4 xi minus 1 and eta minus 1. So when you substitute xi equal to 1, so it will be 0, and when you substitute eta equal to 1, it will be 0. Now for shape function for node 2, so for this node, so it will be xi plus 1 and eta minus 1, and anyhow it will be divided by 4. So you can see that 1 minus 1, this will be plus 2 and minus 1. Okay, let's see, maybe negative sign will come here. So it will be 1 plus 1, and here it will be minus 1 minus 1. So in this case, okay, here we can also write like this, 1 minus xi and 1 minus eta. So here it will be 1 plus xi 1 minus eta and divided by 4. And n3, what is the n3? n3 here, so it will be xi plus 1 and it will be eta plus 1 divided by 2 into 2. So in this case will be 1 plus xi 1 plus eta divided by 4. And similarly n4 will be xi minus 1 and eta plus 1 divided by minus 1, divided by minus 1 minus 1, that will be minus 2 and 1 2. So here it will be 1 minus xi 1 plus eta divided by 4. Okay, so here you can see that we are choosing shape function based on this. Okay, now since we already saw that these all will be a function of x and y, okay, and while choosing the domain it becomes a function of xi and eta. So if we see, like if I want to write b, so earlier it was what? Earlier it was n1x0, n2x0, n3x0 and n4x0. Okay, and this one was 0, 0, n1y 0, n2y 0, n3y 0, n4y, and this will be what? This will be n1y, n1y, n1x, n2y, n2x, n3y, n3x, n4y, n4x. This was, but since we are choosing the we are changing the variable, I mean x, y to xi and eta. So, okay, while changing the variable we already saw that dA equal to dx dy will be changed by using the Jacobian, that will change to d xi or into d eta. Okay, because by the multiplication of Jacobian it will be changed to this. And what is this Jacobian? Jacobian matrix was del x by del xi, del x by del eta, del y by del xi and del y by del eta. Okay, So but here the problem is we have to change this B. I mean, if I talk about this n matrix, I mean shape function matrix, which was what, n1, n2, n3, n4, and okay, here it will be 0 0 0 0, n4 0, n1 0, n2 0, n3 0, n4. Okay, and when you take the derivative, del n by which means that if I want to get del n by del x and del n by del y, or you can also write like n x or n y, then it becomes Jacobian kind of. I mean, if you want to write, then it will be multiply by Jacobian inverse transpose matrix, then it will be converted into the matrix n1 xi 0, n2 xi 0, n3 xi 0, n4 xi 0, and similarly here it will be what, 0, n1 eta 0, n2 eta 0, n3 eta 0, n4 eta. Yeah, so this thing we need to do it. Okay, so which means that if I want to get B, if I want to find B matrix, okay, but here it is a function of x, but later when you change the variable it becomes a function of xi and eta. This derivative becomes a function of xi and eta, which means that first we have to multiply with J inverse transpose, then it will be converted into this. Okay, and later, I mean, this will be equal to what, this, if I want to write like this, then it will be equal to n1 x0, n2 x0, n3 x0, n4 x0, and here it will be n1 y0, n2 y0, n3 y0, and n4 y. Okay, so now, so this is I mean, by multiplying with J inverse transpose, we can write this thing as this. So which means that suppose this is some kind of matrix which is like if I assume this is as n double hat, then if I want to write B matrix, then I can write same thing. Now this will be a function of xi and eta. Then the index position of this I can write what, n double hat 1 1. Okay, n double hat 1 2, n double hat 1 3, n double hat 1 4, and similarly it becomes n double hat 1 8. Okay, and here it will be what, n double hat 2 1, n double hat 2 2, sorry, yeah, n double hat 2 3, and this will be n double hat 2 8. Now what will be the entry? What will be the entry in the third row? So I can write n double hat. N double hat what? So this thing you can see that whatever this is, I have to write this entry first and then this entry first. So what I can write, 2 1, I can write 2 1 and 2 2. So 2 1 n double hat 2 2. Okay, no, 2 1 and 1 2. 2 1 and then this one. Okay, 2 1 and 1 1. Okay, wait, first it will go this and then it will go this, then this. Okay, okay, okay. So first it will go this, then this, then it will go n 3 1 and n 3 2 n 4 1 n 4 2. Okay, so you can see that these are 8 entries. Okay, so it's done. So this is what this is B matrix. Okay, this is all about B matrix. So now you can see that I can directly use this as a B matrix. Where is that? Yeah, B matrix. D is already a constant, so by using the Jacobian it will be transferred into that, and N transpose will be what? N transpose we can change by using the Jacobian again. And yeah, so yeah, in this problem now we will take in this problem, suppose we are taking 4 elements. Case 1, 4 elements case. Okay, for 4 elements. For first we will solve for 4 elements and then we will increase 4, then case 2 for 8 elements. Okay, and also we will visualize how that our physical domain is actually deforming. Okay, now we are also doing one thing, like if we increase the number of elements, then it's not easy to handle the traction boundary condition. Then what we are doing is, suppose in this case, like I'm taking 4 elements. Okay, I'm taking 4 elements, like for the global domain, what is that? For global node, what is that? 1 2 3 4 5 6 7 8 and 9. Then I'm assuming that for this particular edge, I'm assuming for this particular edge as this is as edge 1, this is as edge 2, edge 3 and edge 4. Okay, and similarly for this element, for element number 2, where what is the here what is the global node? 1 2 5 and 4, and here what is the global node? 2 3 6 and 5, and this is the element number 2. And again I'm assuming edge as number 1, 2, 3 and 4. Why we are doing is because when you assemble, okay, so suppose for one element we are applying this integral for the element, okay, for e equal to 1, so that will be b transpose d b transpose sorry b transpose d b into Jacobian del xi del eta, okay, and it will give for this element equal to, and here it will be for this particular it will be n transpose t ds, here also Jacobian and ds, and that body there is no such body force, so we will not use that. So for element e equal to 1, we can see that for this particular element we will have this n matrix, okay, I mean the shape function matrix, and for the shape function matrix it will do a line integral, for the whole path, I mean for path 1 to 2, 2 to 5, 5 to 4, which means that for this line integral the same shape function will run for path 1 to 2, for then 2 to 5, then 5 to 4 and then 4 to 1. Okay, so for the same shape function it will do something like this. So what we are doing is we are creating a edge matrix, where for each edge for each element, suppose for element 1, 2, 3, I mean how many elements are there, so 1, 2, I mean 4 elements we are using, suppose we are using the 4 elements, so 1, 2, 3 and 4, and for the 4 elements what we are doing is we have numbered like bottom edge, then right edge, then top edge and then left edge. So for edge for element number 1 we can see that there is no such traction boundary condition, I mean if it is there is a zero traction on this, which means that there is a zero traction on this edge. So for element 1 we are taking as a 0, there is no such traction boundary condition on this edge number 2, so 0, 0, 0, and similarly for 0, 0, 0, 0. But for element number 3 we can see that the bottom as 0 edge, and here zero traction, here also there is a 0 traction, but here on this edge number 3, the top edge, it has a traction boundary condition, which means that, and what is that, the value is what, 20. So that's what we are doing is we will make an entry of 0, minus 20, okay, and here there is no traction, okay, here for same thing here also 0, 0, 0, minus 20 and 0, which means that whenever that loop will run, then it will be multiplied. You can see that the edge matrix will be multiplied in this case. So that's why whenever take the traction, whenever take the n transpose t, then t will be what? T will be this edge matrix. T will be this edge matrix, so that when it takes the matrix multiplication with row and column, then automatically it will be multiplied for this 1 to 2 edge will be multiplied with 0 and then 0, and automatically when it goes for edge number 3, then it will multiply by this. So which means that there will be only a contribution of the traction boundary condition will be for edge number, for element number 3 and 4, and for the corresponding edge like 7 to 8 and 8 to 9. So while assembly, this edge matrix will help. So we will be using the edge matrix in this case. So it will be very easy to solve. Now, so yeah, it's all about the edge matrix. Then automatically it will be solved. Now let's go to the MATLAB program and we will see how we are using it. So yeah, let's so here you can see that del n by del xi eta is a function of eta and xi. Then after the multiplication with Jacobian, after the multiplication is with the Jacobian, then it becomes a function of x and y, which means that this thing is nothing but del n by del x and del n by del y. So automatically we can use this. So here you can see that after multiplying this matrix with J, then we will take the indices, we will take the corresponding indices to construct a B matrix. So this is all about the B matrix, and now we will see Jacobian. So it is not a very different thing. Here you can see that Jacobian is nothing but the derivative, I mean del x by del xi, del x by del eta, and del x by del eta, sorry, del y by del xi and del y by del eta. So after getting the derivative, we will get the Jacobian. And let's see the stiffness matrix. So again, in the stiffness matrix, it will take a nodal coordinate, whatever the nodal coordinate for that particular element, and order which means the point. Let's write the point here, and it will be used in the Gauss quadrature. Okay, and this is a constitutive matrix, and here what E and nu we are using, let's see this problem. Yeah, 3 10 to the 10 raised to the power 7, nu equal to 0.3. Okay, so then it will take the xi and eta from this matrix, and first it will find a Jacobian, because we have to multiply to change the area which was the function of x and y to convert into xi and eta. And B matrix we will import, and we will give the nodal coordinate as xi and eta. And then we will multiply with Jacobian, WQ transpose C and B, and it will be added into the stiffness matrix. Okay, and now we will see the force matrix. the most difficult part is to handle the traction. So the biggest problem which I faced to write a MATLAB code is to construct the force matrix. Stiffness matrix is very easy, but difficult part is to construct a force matrix. So here in the force matrix, it will take nodal coordinates order. Here also I am writing a point. Points and Neumann is. Here I am writing Neumann is, which means that it will give for that particular element. If we call the force matrix, then based on that particular element, it will give a edge matrix. It will give a edge matrix, which means that it will give that particular row. Which means that suppose for element 1 it will give this row, okay. And actually here the edge matrix is 3 by 3 matrix, okay. It is a 3-dimensional matrix because it has the traction has 2-dimensional. Traction is 2-dimensional, so whatever the entry is will be 2 by 2, which means that I have to write 0 0, I have to write 0 0, and here 0 0 0 0. So it is a 3-dimensional matrix. If it is a 1-dimensional case, then it will be a 2-dimensional matrix, but here in this case it will be a 3-dimensional matrix, which means that there will be one more thing that will be extended in this here, okay. So for the front face, the entry will be 0, and the back face the entry will be 0. But in this case, for the edge number 3, so for the element number 3, the front face entry is 0, but the back face entry is -20. So which means that, for each element, suppose for element number 1, then what it will give is, it will give something like this. So yeah, for element number 3, I am talking about the element number 3. So for this element, the edge matrix will look like something this. Okay. So you can see that it is actually a 3-dimensional matrix. Okay. So it has the row 1 only, but it has one more depth which is inside the page, okay. So that's why it is a 3-dimensional matrix. So here it will take a Neumann edge where q1 is nothing but this thing, okay. This is q1, this is q2, this is q3, and this is q4. So which means that the q1 it will be what? It will be this, okay. q1 will be this, q2 will be this, q3 will be this, and q4 will be this. So that's why it is doing what? Row number 1, but column number 1, but whatever it is, it will be, there will be a column, so it will give whole 3D view of that q1. So and similarly q2, q3, and q4. So q1 will be a kind of column matrix. That will be that for this q1 it will be entry something like this, for this entry will be something like this, and this entry will be something like 0 -20, and for this entry will be something like this. So that for each edge it will be multiplied with the shape function. So here it will be what? Shape function, okay. So then we will call the Gauss quadrature point. Now this h1, h2, h3 and h4 is the Jacobian for the line integral, and we already saw that this is nothing but this h AB is nothing but the length of AB and times 1 by 2 times, suppose the length of AB is L, then it will be L by 2. So whatever it is, so for there are 4 edges, then it will be multiplied by 0.5, and this is nothing but the edge length. Okay, and then it will find the shape function for bottom edge, right edge, top edge and left edge. You can see that. So here you can see that for the bottom edge, the eta should be -1, and it will be xi. And for right edge, you can see that the xi should be 1. Okay, and whatever it is, it will be a xi. And for top edge, the eta will be 1, and for the left edge, xi will be -1. Then it will be stored in N1 bottom, right, top and left, and then it will be multiplied, which means that this whole thing is a line integral for the particular element. So here you can see that h1 is what? H1 is the Jacobian. Then q1 dash, I mean for q1 dash, this means what? Here the traction boundary condition on this edge. Okay, and then it will be multiply N1 bottom. Okay, and h2. Okay, yeah, it's done. And here it will be a for edge number 2, and this thing is for edge number 3, and this thing for edge number 4. Okay, and then will be added into the traction in initial matrix. Okay, and for each element it will run the loop. Okay, so this is all about the force matrix. Now let's see the driver code. So here it is a driver code. So first what I am taking is, I am taking 4, I mean total number of elements as 4, and this is the coordinates of the initial nodes. Okay, whatever in the physical domain it was. In the physical domain, the coordinates was 0, 0, 2, 0.5, 2, 1 and 0, 1, and this will be stored into x1, y1, x2, y2, x3, y3 and x4, y4. Then it will initialize x coordinates to create a mesh. Okay, based on that it will create a coordinates of all mesh, so coordinates of all elements, and it will be stored here. Okay, let's run this code up to this point, and we will see how many values it is storing. Okay, so here you can see that the x coordinates for each element. Okay, this is for the element number 1. Yeah, so here it is the coordinate. So suppose there are, okay, actually what I am doing here is for each row we have created 4 elements. So what I am doing is, I will create only two elements first, then we will extend. So yeah, let's run up to till this point and we will see. Yeah, x coordinates we will see that for this element, okay, whatever the coordinate will be, like 0, 1, 2, this is the coordinates. I mean based on this element, this is not the elemental coordinate, actually based on this mesh, what is the nodal coordinate. So nodal coordinates, we can see that the x-axis along this line, which will be 0, 1, 2, and along this line 0, 1, 2, and along this line also 0, 1, 2. But the y coordinates will be what? 0, 0.25, 0.5. Okay, sorry, yeah, 0.25, 0.5, and here will be 0.5, 0.625 and 0.75. okay, similarly for this. Okay, so now, yeah, now here we will see how it is creating a mesh. We will run to this point. Okay, so here we can see that it has created 4 elements. Okay, here element 1 2 3 and 4. Okay, so whatever we have imagined. Okay, now it will create a edge matrix. It will create a edge matrix, and here what I am trying to do is I have created a function where to create a edge matrix, what it will do is it will find based on the boundaries. You can see that the left boundary is the left boundary equation is this, right boundary equation is this, top and bottom boundary will be this, and whenever the length of the boundary will be less than the tolerance, which means that this tolerance I have created is nothing but the 0, but it is difficult to find 0. So that's why what it is doing, it whenever the boundary is less than this, then it will give the nodes. So here you can see that the node we have already created. Let's see what are the nodes. So here these are the nodes. Okay, and based on this, these are the nodal coordinates. So you can see that for node number 1 this is the coordinate, node number 2, and similarly for till the node number 9. So you can see that what it will do is along this line, I mean the whole coordinate along this line, it will try to find the index, and based on that it will mark as edge matrix. Okay, so let's run this code till this point. Okay, and we will see how the edge matrix is calculated. So here you can see that there are 4 elements. So based on that it has created an edge. So here it is what, here it is the front, here it is the front face, and here it is a back face. So here you can see that there is no such Nymon edge for the front face, but for the back face it has the Nymon edge for the element 2, 3 and 4. So that's why it has the entry -20 and -20. Now if we will move to that, the main core thing of our code. So here I have initialized k global, f global, then it will go into the stiffness matrix and it will calculate. Let's see, let's run this code till this point. So now it has find. Now it's about the fixed node. Okay, so what is the fixed node? Based on this image, the fixed node is what? The left boundaries. Okay, all the left boundaries. And what is the left boundaries? Okay, let's see here what is the left boundary, right boundaries. So here you can see the left boundary is nothing but 1 4 and 7 node. Okay, and bottom bound is what? Bottom boundary is what? 1 2 3, and right boundary is what? 3 6 9, and what is the top boundary? 7 8 and 9. Okay, and so based on this fixed node is what? 1 4 and 9, that is nothing but the left boundary node. Okay, and this is the free node. So and now it will initialize the displacements, which is the all 0, and this has given a Dirichlet boundary condition which is on the left boundary, and now it will find k reduced, f reduced, and it will solve, and then it will create then it will find a reaction force. Okay, so we have found that. Now it is the time of post processing. Okay, so post processing, I mean you can also find that, I mean if I get the u for the case of post processing, we already got u. Okay, based on that u, you already know that we need to find delta u, and delta u is nothing but what? b times u. Okay, and delta u, when you find the delta u, which means that this is our strain, and if you got the strain, which means that I can also get a stress. And what is the stress? Stress is d times strain, and that is nothing but d times delta u. So it is easy to find. Now we will run the whole code and we will see the result. Yeah, and we will also see figure 1 here. Yeah, there is one more thing which I want to mention here is, suppose for each node it will have a sigma 1, sigma 2, sigma xy. Okay, so it's very difficult what is actually suppose if we want to design something, I mean some part of the body, and it has, after solving the FEA problem, then you will, for each node you will get what? Sigma matrix, that is sigma xx, sigma y, and sigma xy. But which part is very critical? So it's very difficult to judge based on this matrix. Then what we will do is, we will find the von Mises. We will find the von Mises stresses. And what is the formula to find the von Mises stress? So von Mises stress is nothing but it is a kind of effective stress. When you find the von Mises stress, then it will be very easy to judge which part is very critical. So here we'll give you the formula. Yeah, so here it is the von Mises stress. So this is what? Sigma x square, sigma y square minus sigma xy into sigma xy plus 3 times sigma xy square. So based on this we will find the von Mises stress. And here also you can see that strain is what? B times u local. Okay, whatever you got it. Okay, and stress local is what? C times strain local. Okay, and based on this we found that. And here it is a heat map, strain field heat map. Then here you can see that this part has the maximum deformation. Okay, and this part has the lowest deformation. Okay, because it is fixed at the end. And this part has the maximum stress. You can see that this part has the maximum stress and this part has the minimum stress. Okay, and here also we can see that how the part is actually deforming. So here you can see that node point 8 will move to here, and this point will move to here, and here you can see that how it is deforming. Now what we will do is we will increase the number of points and number of elements. We will see how smooth it is going. Suppose I am increasing to 100. Okay, I think it's too much. So let's see. All part is actually it is doing so much calculation. So you can see that yeah. So again you can see that this part, this point has the maximum stress. Okay, similarly here, and you can see that how the part is actually deforming. Okay, wait, what we will do is we will close all and we will run it again, and all this point, and we will decrease. I mean, if along x it is 10, then there will be total 100 elements. Okay, now here you can see that how the part is actually deforming. Okay, so yeah, so it was all about this problem. I mean, this problem is very a kind of standard 2D problem. You can zoom it, and it has everything. I mean, the solution of the problem, post processing, and everything, and visualization also. You can see that how the part is actually deforming. So this problem you can think it as a complete finite element. I mean, for the linear for the linear elasticity, this problem is a kind of complete solution. Okay, so yeah. Okay, so let's end this session, and in the next week we will solve some transient problem. I mean, based on it is a function of time also, not only a function of x and y, it will also a function of time, and we will do how the eigenvalue thing comes into the picture. So yeah, see you next week, and we will try to solve another kind of problem. Bye bye.